So we have two blocks that are connected by a light rope over a frictionless pulley. Block A is 8 kilograms and rests on a horizontal surface with a coefficient of kinetic friction of 0.2, while block B is 5 kilograms and hangs vertically off the edge of the table. So the first thing I want to do is I want to draw a picture of this, right? So I have some table, there's a pulley on the edge of it. Block A is sitting on the top of the table and it is connected with a rope to block B that's hanging off the edge. The next thing that I want to do is I want to list out the information in this problem. So the only information that we have in this problem is we know that the mass of block A is 8 kilograms. We know that the mass of block B is going to be 5 kilograms. We have that our coefficient of kinetic friction is 0.2. And as always, we have G is equal to 9.81 meters per second squared. So I want to consider also what type of problem this is. It looks like the only thing we have here is forces. We don't have anything else. So this is going to be a forces problem, meaning that we will need to use Newton's second law. F is equal to ma. Now before I figure out what it wants us to solve for, I'm actually going to break this picture down into two separate pictures. I want to draw the free body diagram, right? Draw the forces for block A, and then I want to draw the forces for block B separately. So I'm going to start with block A. So I have block A here, and it is sitting on a table. There's a rope attached to it, and for the purpose of this, I'm just imagining that my rope goes off to infinity. All I'm doing is looking at block A and the forces that are acting on block A. So now I want to draw what forces are on here. Well, I know that we have the force of gravity that's acting downwards, and also because this block is sitting on a table, right, it's sitting on a surface, there has to be a normal force perpendicular to the surface that it's sitting on. So I also have the tension force from this rope going in the positive x direction. The next thing that I need to consider is this force that is going to be caused from the kinetic friction coefficient whenever this object starts to move. So in order to determine what direction my frictional force goes, I need to think about the motion of this object. So even though block A is greater than block B, if this were to start to move, it would only move in this positive x direction. Since my frictional force opposes the motion of the object, my frictional force is going to be going in this negative x direction. Now before I even consider what's going on with block B, I want to create the equations of motion for this object. So I need to think about the summation of forces in the x direction, and I need to think about the summation of forces in the y direction. I'm going to go ahead and set these equal to mass times acceleration in the x direction and mass times acceleration in the y direction, because we're going to start with Newton's second law. I also need to now replace the summation with an actual list or summation of the forces acting in each direction. So in the x direction, I have a tension force and I have the force of kinetic friction, and this will be equal to mass times acceleration in the x direction. And I'm going to deal with my directionality in my third step. I do this because for me, I know that I will always list the forces first and then consider the directionality. I know that this is the process that I use, so I don't ever have to worry about, did I already incorporate the directionality? Did I forget that? Did I mess something up? Because I'm consistent with how I do this. So in the y direction, I have my normal force and I have the force of gravity, and this will be equal to mass times acceleration in the y direction. I should actually go ahead and put the subscript A here. Although I know that I'm only looking at block A right now, this might be important later. So the next thing I'm going to do is I am going to consider the directionality here. To do this, I'm going to use just a normal coordinate system where we have the positive x direction on the right-hand side, the negative x direction on the left. Negative y is going to be at the bottom, positive y is going to be at the top. So my tension force is moving in the negative x direction, so it's going to be positive. My frictional force is going in the negative x direction, so I'm going to have minus the coefficient of kinetic friction. And if this object were to move, we said that it was going to be moving in that positive x direction, which means that the acceleration would stay in the positive x direction, so this will be a positive value. For the y direction, my normal force is going in the positive y direction, my force of gravity is going in the negative y direction, and if this object were to move, we said that it was only going to move in the positive x direction, right? If this object starts to slide on our table, right, we have our table, these are connected with a rope. If this starts to move, the object is going to move only in the x direction. It's not going to levitate off of the top of the table. It's not going to sink down into the top of the table. There's going to be no motion in this y direction, meaning that there's no acceleration in the y direction, meaning that we can set this equal to 0. Now the next thing that I want to do is I want to see if I can replace any of these variables in these equations with a more specific version, right? So I know generally that my force of kinetic friction is equal to my coefficient of kinetic friction times the normal force, and I know that the force of gravity is equal to the mass times g. In this situation, I am not considering directionality. This is not a vector. I do not have a vector sign on top of it. So that's why I'm using g, which is a scalar, instead of acceleration due to gravity, which is a vector. This is a scalar value. I have incorporated my directionality already in my summation here. So I'm going to replace my frictional force with tension minus my coefficient of kinetic friction times the normal force is equal to the mass of this object times the acceleration in the x direction. And I'm going to replace this Fg with the mass of the object times g, and this will be equal to 0. I see already that I can simplify or make this equation in the x direction more specific by replacing my normal force with an equation for the normal force that comes from the y direction. So we have a system of equations now. I'm going to move this mass times gravity over to the other side, so we get that the normal force has to be equal to the mass of the object times g, and I can plug this in for the n in my equation for the x direction. So I get that the tension minus my coefficient of kinetic friction times my mass of the object times g has to be equal to mass of the object times acceleration in the x direction. This is the most specific I can make these equations right now. Now I'm going to think about the other object. I'm going to think about block B. Block B is a lot easier because it's dangling off the edge of a table, right? So if this object were to move, it could move up or it could move down, but there's going to be no left-right motion, meaning that there's going to be no motion in the x direction. So the summation of forces in the x direction is mass times acceleration in the x direction. Because this isn't moving in the horizontal direction at all, it's not moving in the x direction, I have no forces in the x direction. But what about the y direction? The y direction, we will have some sort of motion, so we need to consider the forces that are acting on this object. So we have the force of gravity that would pull it down. We have the tension force in the positive direction, And that's all. We do not have a normal force here. This is one of the biggest mistakes that I see students make, is that they assume that if we have a force of gravity, that there will be an opposing force that is the normal force. Normal forces only occur whenever you are sitting on the surface of an object. Because this is dangling mid-air, there is no surface for a normal force to be created. So there is no normal force in this situation. Biggest mistake I see students make all the time. So now I want to go ahead and replace my summation in the y direction with tension plus the force of gravity is equal to the mass of this block times the acceleration in the y direction. Well, now I need to consider directionality. So I'm going to go ahead and I'm going to think about this picture again. We have block A, it's connected by a rope to block B. If this object were to start to move, right, think about block A. If block A is going to move at all, it has to move forward. It can't move backwards. There's nothing pulling it this direction. Either it's going to move forwards or it's not going to move at all. What about block B? We said that block B, if it was going to move in this picture, it could move in the positive or in the negative direction. Well, if block A can only move forwards, that means that this rope is going to start to come down, meaning that block B is going to go in the negative direction. In order for block B to move upwards, block A would have to move in the negative x direction, and we said that that's impossible, right? Either block A is going to move forwards or it's not going to move at all, meaning that either block B is going to move down or it's not going to move at all. So my directionality here for the acceleration has to be in this negative y direction. So my tension is in the positive y direction. My force of gravity is in the negative y direction, and if there's going to be any motion at all, it is going to be in the negative y direction, meaning that this acceleration would have a negative directionality to it. The next thing I'm going to do is I'm going to replace this Fg with the more specific version of the equation. So mass of block B times g is equal to negative mass of block B times acceleration in the y direction. This is as simplified as I can make these equations. Once I have these equations, I'm now going to figure out what it wants me to solve for. Because I have to do all of this no matter what it's asking me to find. All of this has to occur for a forces problem no matter what variable it wants me to solve for. So the first thing it wants us to determine the acceleration of the system. So I want to find the acceleration of the system, and it's also going to ask me to find what is the tension in the rope. So I want to find the acceleration of the system. Well, I have this equation for block A that involves acceleration, and I have this equation for block B that involves acceleration. So I'm going to go ahead and rewrite those. So I have that, we'll do this, well, we know it's block A because we have subscript A here. So I have the tension minus my coefficient of kinetic friction times the mass of block A times g is equal to the mass of block A times the acceleration in the x direction. And then I also have an equation here that says the tension minus the mass of block B times g is equal to negative mass of block B times the acceleration in the y direction. I cannot just solve one of these equations for acceleration because I don't know what tension is and I don't know what the acceleration is, meaning that I have two unknowns, and the same thing for the equation that I have that describes the motion of block B. Whenever I have two unknowns, but I have two equations, right, I can use a system of equations and plug one in for the other. This means that I have to choose whether or not I solve equation, well, it doesn't really matter. If I solve one equation for t and plug it in, or if I solve the equation for acceleration and plug it in. Well, because I want to determine what the acceleration is, I don't want to get rid of that variable. I know that these blocks are connected together, their tensions have to be the same. I have incorporated directionality into both of these. None of this is vectors. These are all now scalar numbers, meaning that the tension in block B, the rope acting on it, and the tension acting on the rope in block A have to be the same, right? Because they are connected with the same rope. And we imagine that the tension moves undiminished through this rope. So I'm going to solve the equation for block B for tension. So this means that my tension is equal to the mass of block B times G minus the mass of block B times the acceleration in the y direction. I can now plug this in to the equation for block A. So if I'm going to plug this in, I will get the mass of block B times gravity minus the mass of block B times the acceleration in the y direction minus the coefficient of kinetic friction times the mass of block A times G is equal to the mass of block A times the acceleration in the x direction. There's one more thing I need to consider here, right? And that is I have an acceleration with a subscript x, and I have an acceleration with a subscript of y, right? I have the acceleration on block A, which is in the x direction. I have the acceleration on block B, which is in the y direction. These are now scalar numbers. I already incorporated the directionality in the equations whenever I wrote these equations out. So, the magnitude of the acceleration in the x direction on block A and the magnitude of the acceleration in the y direction in block B have to be the same. That's because they are going to be moving together, right, with this rope. This means that AY is the same thing as AX. I'm just going to replace that with A. So the mass of block B minus the mass of block B times the acceleration minus the coefficient of kinetic friction times the mass of block A times G is equal to the mass of block A times the acceleration. Since I'm solving for acceleration, I want to get acceleration by itself on the left-hand side. So I am going to move this to the left, and I'm going to move these two over to the right-hand side. So I get the mass of block A times the acceleration minus the mass of block B times the acceleration is equal to the coefficient of kinetic friction times the mass of block A times G minus the mass of block B. I can simplify the left-hand side by pulling out the acceleration. And then I'm going to divide both sides by the mass of block A minus block B. And now I can plug in my information. So I had that the mass of block A was 8 kilograms, I think. The mass of block B, I think, was 5 kilograms. My coefficient of kinetic friction was 0.2. G is 9.81. I'm not sure, though. Let me check. 8.5. 8.5. Yes, so now we can just plug this information in. And when we punch this in a calculator, we get that the acceleration is 3.57 meters per second. I don't have a vector sign on this because this is just the magnitude of the acceleration. The directionality depends on if I'm talking about block A, which would be in the positive x direction, or if I'm talking about block B, which would be in the negative y direction. So this is just the magnitude of the acceleration of this system. The next thing it asked us to solve for was it wanted us to solve for tension. This is going to be a lot easier because we can go back to these two equations that we have here and figure out which one is easiest to solve for t. It looks like this equation is going to be easiest, not really for any reason other than the fact that it has one less variable in there. So we have that tension minus the mass of block B times gravity is equal to negative mass of block B times acceleration. I'm now just going to move everything over to the right hand side. So we get the mass of block B times g minus the mass of block B times acceleration. I'm going to simplify this just because it's my personal preference. And then we can plug in our values here. G is 9.81 minus the acceleration, which was 3.57. I don't have to worry about directionality. I already incorporated it into that equation. And we get that the tension is 31.2 newtons. I like to double check myself sometimes, honestly, just to make sure that I get the same value or the same value with rounding errors. So I'm going to rewrite that equation for block A and just plug everything again and make sure that I get the same thing. And I got 44.256. That means that there's an issue here. These should be exactly the same. If they're not the same, there's a problem with our value for acceleration. So I want to look back at the work that I did for acceleration and figure out the first thing I want to do when I encounter an error is I want to check to see if I actually did some part of the calculation wrong, like if I punched it in the calculator incorrectly. And I didn't punch it in the calculator incorrectly, so the next thing I need to do is I need to go back here and I need to look at my algebra. I need to figure out if algebraically I did something incorrectly. I found my error, and my error is a really, really simple mistake. You probably caught it while I was doing this, but this is a good reason as to why I do all of this algebra before I punch anything in the calculator. And my error is right here. I forgot the G. So I'm going to put my G back in, which means that I will have a G here, I'll have a G here, I'll have a G here. This should be 9.81. But then I get a negative number. I get negative 11. This doesn't make sense, right? Because I shouldn't have a negative number. I already have directionality included. I should have a positive scalar value. So the next thing that I need to do is there's a second error. So, I guess I should bring you into my thought process. What I'm trying to do here is I'm trying to figure out if this block is even heavy enough to move block A. The problem is that, okay, if there's nothing, if there's no friction, yes, it will slide. Even the smallest amount of mass from this block would cause it to slide. But like in real life, there's some sort of static friction here that would occur, right? Because, right, force of kinetic friction, static friction, and then we go, ooh, and then we move into the kinetic friction regime. I want to know if we have enough force to actually get it to start moving. So, the problem is that if I assume that block B is not moving, I also have to assume that block A is not moving. But I don't have a value for static friction. I could I got it. Okay, I could figure out what amount of tension is necessary to get it to start to move. So I'm gonna scratch that idea. I'm gonna think about the forces on block A. So we had, I'm just gonna rewrite the thing that was up at the top. Tension minus the coefficient of kinetic friction, mass of the object times G. And let's assume it's not moving. Or we can't really assume that it's not moving. I'm going to assume that this force of motion forward, it's MA, is very, 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 very small, and ignore it. So, tension in order to get this to be any number above 0, even for it to be moving, the tension caused by block B hanging is going to have to be equal to, at a minimum, right? It can be significantly larger than this, but at a minimum, it's going to have to be 15.96 newtons, and just the force of gravity is greater than 15.96 newtons. It will move. So then what's the issue? Okay, after way too long, I figured out where the error is, and it is an algebra mistake right here. I tried to do way too much at the same time. And I made it a really simple, really stupid algebra mistake. So, I am going to move this to the right-hand side and flip the whole equation around at the same time. MA A plus MB times the acceleration is equal to MBG minus mu sub K mass of A times G. I had it backwards. So a simple mistake with algebra turned into, honestly, about a 20-minute ordeal of me trying to figure out what in the world I did wrong. And it was just a stupid, simple algebra mistake. And we get 2.56 well, I guess it would round up to 7 meters per second. Now if I do 2.57, we should get the same value here. 36.2 newtons. And please let this be the same number. Woo! 36.3 newtons. It's within a rounding error. So, the acceleration is 2.57 meters per second. The tension is 36.3 newtons. So, that's how we solve this problem. I'm going to leave in all of my mistakes because I think that sometimes seeing how other people go approach finding their errors and working through it can be helpful, right? It can show you different ways that you can go about finding your own errors. Because, unlike many YouTube videos, the purpose of this is not to give you the answers for your homework for your college physics class. It's hopefully to help you actually learn how to solve these problems.